energy. So then what do you think you could also make a relationship between thermal expansion and melting point? If a material has a high thermal coefficient of expansion, do you think its melting temperature would be high or low? Yeah, perfect. High melting point, low coefficient of thermal expansion. And that's because both of these are directly related to bonding and bond strength. What's another property that we've talked about that's directly related to bond strength? Yeah, I'm just going to assume that E is elastic modulus. Great. So again, like there's all these little things, in the beginning of the semester, um, when I said bonding determines everything, this is, what I was talking about. Like now we know about the bond strength of a material. We might know its melting temperature, then we can infer its bond strength. And now we're going to know about its coefficient of thermal expansion. We're going to know if it's soft or stiff. I mean, that's pretty cool, right? Like all we need to know is a melting temperature and we can infer all these other things because then we know something about bonding, right? It's pretty cool. All right, so that's thermal expansion. Electronic properties, that's where, electronic and mechanical properties, that's where we spent a lot of our time in this last block. So when we talked about electronic properties of materials, we looked at Ohm's law. Of course, from a circuits course, you all are probably all pretty familiar with, V equals IR. And then we rewrote that in terms of material properties, say resistivity or conductivity. So that, excuse me, that really gets me to this next bullet point, which is resistivity versus resistance, where, resistance would be you have some resistor, you measure its properties, and then resistivity would be an actual material property. So resistance might characterize a specific device. Resistivity is a fundamental material property. If you go back up here, think about structure property effects. If I tell you you process a material via some method, like you quench a material, what do you think is going to happen to its conductivity compared to an annealed sample? Which would have a higher conductivity, a quenched alloy or an annealed alloy?
Probably an annealed alloy because the grain. Okay, so there would be the larger grain size means there's less places where the flow of electrons are interrupted.
Yeah, so if you have an annealed alloy compared to a quenched, it's going to be more homogeneous. There's going to be less scattering. Great. So then the next thing we can think about is, electronic conduction. So if I think about electronic conduction at its fundamental, what two things do we need for a material to be an electronic conductor? We need charge carriers. Yep, great. And those charge carriers need to be electrons or holes in the case of semiconductors. And what do we need to what's special? What do these charge carriers need to be able to do?
Move.
Exactly. So you now know that for conduction to occur, you have to have charge carriers and they have to be able to move. So when you talk about electronic conduction, you have to have electrons or holes and they have to be mobile. And now if we look at different materials, we can draw band structures, and those are going to determine whether or not we're going to have electrons that are available to conduct. And then, other properties of the material may impact their mobility, right? So know how the band structures differ for metals, insulators, and semiconductors. If I were to ask you to draw the band structure of any of those, labeling things like band gap, Fermi level, or Fermi energy, I would hope that you would be able to do that. Okay. And then, excuse me, if you think about electron mobility, for these different types of conducting materials, think about, well, what happens as you increase temperature? So if I increase temperature in a material, what tends to happen to the electron mobility? So if you add thermal energy into our system, we're adding more vibrations. What do you think that'll do to scattering?
Increase it.
So mobility actually tends to go down
But
when
scattering
we
increases,
when
right?
we yeah, when we increase temperature. So what I'm seeing a couple of comments, people are saying increases to a certain point, but I think what you might be conflating is that if you have a semiconductor, you can sometimes get more charge carriers as you increase temperature, and that their conductivity can go up. However, the mobility will go down.
And
Typically mobility goes down as mobility goes down as scattering increases, and
so,
scattering will always increase with increasing
so
temperature.
is this why computer chips have to be cooled down to function properly, and they get slower as they heat up?
Yeah, I mean that would probably be one way. I mean the other thing too is a lot of these silicon chips, like, they don't tolerate high heat. I mean a lot of the thermal energy is lost, but yeah, they would make things less efficient. And that's why, like, if you has anyone here ever had the good fortune to get to tour the supercomputer on campus? It's out on East Campus off of Waldo Road. Has anyone ever been over there? Not yet. Well, if you ever end up getting to tour there, wear a warm sweater because it is Arctic in there, because they have to keep all the computers cool enough. But but yeah. Um so okay, cool. So anyway, so that kind of what we just ended up having was a little bit more of a broader discussion, where if you now think about what's going to happen to the electronic properties of a material with temperature, you can think about, okay, well, what's the effect of temperature on charge carriers or mobility, and that will help you come up with the end answer. So for example, if you have a metal, what do you think is going to happen to the conductivity as you increase temperature? Is it going to go up or down? So if I have a metal, what can I say about the number of charge carriers as I increase temperature? Increase, decrease, or stay the same? Same, right. Because they're all free electrons as a function of metallic bonding. So we've got the same number of carriers, and now what did we just say would happen to the mobility? It decreases. So then what happens to the conductivity of a metal as we increase temperature? It decreases, right? Now, on the other hand, if we think about an intrinsic semiconductor, what happens to the number of carriers as we increase temperature? They're going to go up. So now with an intrinsic semiconductor, we can actually get some slight increase in conductivity to a point. And that point where it's going to sort of plateau is when scattering would start to dominate. Cool. So this is like a really easy thing where, or not easy, but like a concept where you can say, okay, I've got this equation, right? And now I know that conductivity depends on two things, carriers and mobility. And now you can just step yourself through what happens to each of these as temperature changes. And I encourage you to think about those types of things throughout. And if you ever get stuck on an exam, really go back and say, like, okay, well, let's start at the beginning. What do I need? Okay, what happens to those things that I need as I change conditions or whatnot? Okay. Um, so ionic conductivity, you know, as you all know, I like to be kind of lazy. So that's why I try to get these things down to their basics. So if I think about ionic conductivity, this is diffusion and an applied electric field. I already know a lot about diffusion because we learned that for the last exam. And now we just have to think about diffusion and an electric field. So what do we need for ionic conductivity? We need our charge carrier, which is what?
Ions?
Perfect. And then those ions need to be able to move. So if we're talking about diffusion in an electric field, what's going to make that better? What's going to increase ionic conductivity? What increases diffusion, for example?
Need open sites?
We need a space to move into, right? So if we had an oxygen ion conductor, we'd want oxygen vacancies, right? And then what do you think would happen? What would be the temperature dependence of ionic conductivity? Is ionic conductivity going to, yeah, it's going to increase with temperature because it's just diffusion. It's diffusion in an applied electric field. So this is all what you learned before, and now we're just using an electric field to control the direction of that diffusion. Does that make sense? Hearing no complaints, I'll go with hopefully. All right, semiconductors. We've already talked about this a little bit with our other conduction, but you have if you want to think about the mechanisms for semiconduction, we can really think about our band structure. We have a valence band separated from our upper conduction band by some band gap that's small enough that an electron can be excited. Intrinsic semiconductors, those are ones that just semiconduct on their own, things like silicon, germanium, some of our compound semiconductors, the 3 5s and the 2 6s. And then we can also try to make those intrinsic semiconductors better by adding dopants. And when we add dopants, they become an extrinsic semiconductor. Okay. And we had some homework problems, and I don't remember if it was a breakout problem as well at the moment, but looking at different materials and identifying, is this an N type, a P type, or an amphoteric dopant? So I would definitely be able to do those and then know how to determine the conductivity for both of those. So of course, in an intrinsic, your conductivity is going to be a function of both the electrons and the holes. If you have extrinsic, whatever you dope with is going to dominate. So an N type, you care really just about the number of electrons and their mobility, P type, holes and their mobility. And then of course, we also had our oxide-based semiconductors, which we most often see in what region of the periodic table, what types of cations? What kinds of metals tend to transition metals? Perfect. Yeah, because the transition metals tend to have multiple oxidation or valence states, and that can lead to the generation of charge carriers. Good. Okay, so if you have an old version, and I updated it online this morning, there should have been a return where right after semiconductors. So this electrical insulator should be its own section. So if you're looking at an old version of the study guide, I apologize for that. It is corrected as of probably like half an hour ago or an hour, 45 minutes ago. So the next thing we talked about were electrical insulators. So mechanisms for insulating, not having mobile charge carriers. So you have this band structure that makes it impossible to conduct. That would be a mechanism for insulating behavior. And then depending on the insulators, we can have electronic isolation. In electronic isolation, you could think about, say, the wrapping around a wire. We could also have dielectrics, our high dielectric constant type materials that are useful for things like capacitor applications. And then fundamental to dielectric behavior is the formation of an electric dipole. When we have a dielectric or a capacitor, what we're really thinking about is a material's ability to store energy in the form of electric fields. And that electric field is the dipole in the material, right? It's a charge that's separated over a distance. And we talked about a number of different types of polarizations, and we had both breakout problems and and homework problems looking at different types of materials and saying, hey, what types of polarization are present, or what is the dominant type of polarization? So if I were to give you any material, do you feel comfortable telling me what the dominant type of polarization would be? So if I give you this first polarization, electronic, what kinds of materials will we find electronic polarization in?
Like all.
Exactly. What about orientation polarization?
Orientation polarization, probably like place substances that already have a dipole, and like with water has an intrinsic dipole, so
Perfect.
orientation
Perfect.
polarization would flip the poles so they'd be all in sync instead of being randomly aligned.
Well, be careful with that last thing. So an orientation polarization, you have a dipole that comes up usually to the structure of a molecule, You suggested water, as did Ethan in the chat, and Claudio said polar. So this is all correct. But if you don't have an applied electric field, the dipoles will be random. It's that they'll align with the
Yeah,
needle.
that's what I
So
meant. So you
yeah,
need to
so
have something to align them, otherwise there won't be an overall dipole.
correct, correct. So, and if you have some material that has orientation polarization, it also has electronic polarization. But what's the dominant polarization type? It's always going to be the biggest type. So orientation polarization is larger than electronic. And you can think about that because if polarization, we define it by the magnitude of the dipole. So you can think about the magnitude of the charges and the distance between them. So as you go from electronic, where we're on an atomic scale, to orientation, we're on a molecular scale, you can hopefully see how these dipole moments are increasing in magnitude. When we talked about space charge polarization, if this is really, you can get charges trapped during processing, you know, um, due to ionization or irradiation. You don't tend, well, unless you're working in sort of, space materials or nuclear materials. This may not be something that you're going to have to worry too much on your day-to-day basis. But then we also talked about this atomic or ionic polarization. So you'll see ionic polarization in any material that has ionic bonds. And that would be, something where, say you have salt, you apply electric field, there may be a slight shift of the ions from where they want to be in the lattice, forming these small and reversible dipoles. um, and they could end up canceling, they often end up canceling out over the macroscopic range of a material. Or you could have atomic, where you have something like our perovskites or our non-centrosymmetric structures, where you can support a permanent dipole in the material. So as you sort of identify what a material might have, the dominant one is, as I said earlier, it's always going to be the largest. Space charge is really more relevant for very specific applications. Like if you process a material in such a way that you get trapped charges, you see it more often if you're dealing in like environments that have irradiation. It's a very unique situation, and for the sake of this class, I probably would not be giving you a scenario where that was the dominant mechanism. Okay, any other questions before we keep cruising? Okay, so the dielectric constant is a measure of how easy it is to polarize a material. So it's really saying, if I put this material in an electric field, how easily is it polarized? Okay, and they're going to be both temperature and frequency effects. So I would be aware of these. We had a homework problem in particular where we looked at frequency effects. So why is frequency important for dielectric materials? You have these dipoles that have to move, right? So if you're moving your field too fast, if it's faster than the atom or ion can respond, then you're not going to see any benefit of that type of polarization. Okay. So electronic polarization is the least susceptible to frequency. Atomic or ionic, where you actually have to have time for an atom or ion to move in your structure, is going to take the most time and therefore be the most susceptible. In terms of temperature effects, we saw cases where dielectric constant could increase some with temperature, right? As you have the mobility of the ions, but you also have to be aware of phase transitions, such as in the perovskite structures, where you go from a tetragonal to a cubic structure. And if you go to a centrosymmetric structure, what's going to happen to your ability to support a permanent dipole?
It's going to vanish because the
Perfect.
center it's symmetric. So
Yep, exactly. Exactly. You have to have a non-centrosymmetric structure in order to support a permanent dipole. Okay, and then we went and talked about a number of properties related to insulating behavior. So we talked about capacitance. So the best capacitors are going to be those with the highest dielectric constants. Okay, So that's, capacitor applications. We looked at the polarization as a function of electric field for, hard and soft capacitors. And then we talked about something called dielectric strength. And this is an easy one to get tripped up on, but do you all remember what dielectric strength is? Or maybe I'll ask a different way. Are the best capacitors the strongest dielectrics, or do they have the highest dielectric strength? Actually, they don't. So a capacitor has a high dielectric constant, but dielectric strength talks about the ability of a material to maintain its insulating behavior even at very high fields. So if you think about a dielectric, the highest dielectric strength materials, these actually tend to be our polymers and our epoxies, because you just have these covalent bonds. It's going to be really hard to generate a charge carrier. So if you were measuring the dielectric strength of a material, what you do is you basically put it in an electric field and crank it, and see at what point the material breaks down, and you start to get the flow of current. Okay. If you want an example that you may have seen recently of dielectric strength or dielectric breakdown, if you will, is if you ever see lightning, that's a case of the dielectric breakdown of air. So the highest dielectric strength is often not your highest dielectric constant materials. Okay, everyone good with that? All right. So the next thing we kind of talked about was dielectric loss. Um, Basically, it's anything that would prevent your material from being a perfect insulator. So what might what always gets in the way of, or what often gets in the way of perfect materials? Defects, right? So if you have a dielectric material, say you have some transition metal that you think should be insulating, but you get a little bit of a defect in there that can be a charge carrier. That's going to be a mechanism for dielectric loss. And we often see this dielectric loss, in terms of a phase lag as we're measuring the properties of these materials. So if you put a dielectric material into an applied electric field, say it's got a sine wave, what you'll find is you have some slight lag in the material responding. And that's just because you have some losses. So the material absorbs some of that energy due to loss before it responds. And the magnitude of that loss tells you about, you know, the the magnitude of that phase lag tells you about the loss. Okay. The next thing we talked about were our high dielectric constant materials, which went right into these perovskites, which was really just I think a fun way, because I love perovskites. I think they're a fun material system. But you could see how playing with different cations can affect the structure, and that could affect whether or not the material has the possibility to be ferroelectric or not, or piezoelectric or not. And we could calculate that using that Goldschmidt tolerance factor. When we did piezoelectricity, again, the piezo is really a fancy way of saying stress or pressure induced electricity. So you squish on a material, and you get a polarization. Anyone that has a gas grill, or a push button type um, gas grill, that's usually a piezoelectric mechanism that you press on that, and then that strain would generate a voltage. There's also pyroelectrics, where now a temperature gradient induces a dipole. And then we have our ferroelectrics. These are the materials that have a permanent dipole. All ferroelectrics are piezoelectric, but not all piezoelectrics are ferroelectric. And we had that little flow chart there's a flow chart in the slides. All right, how are we on that as we head into mechanical behavior? And orthorhombic structures can also exhibit piezoelectric properties, because because you have in an orthorhombic system, none of your lattice parameters are equal, which allows you to have a lack of a center of symmetry. So orthorhombic structures can also be piezoelectric. Any other questions? Okay, so mechanical behavior, this is something that you all have probably, well, I know you've seen before in 3010. Some of you are in mechanics and materials, and you know these sorts of things have come up before, and of course we've looked at it with slightly different, with some amount of review and then some amount of new lenses as well. um, so we talk about elasticity, stress strain relationships. We already talked about how the elastic modulus is directly related to bonding. um, and one of the things we talk a lot about, have talked a fair bit about this semester, is whether or not a property would be isotropic or anisotropic. So if I gave you a material and I showed you a grain structure, do you think you would be able to tell me if its mechanical properties were isotropic or anisotropic? What kind of grain structure would be isotropic?
Like fine equiaxed grains.
Yeah, I mean, so you just said fine equiax grains. What about coarse equiax grains?
Yeah, I suppose just any equiaxed grain.
Perfect. And now if you see any sort of preferred orientation, say elongation of grains in one direction, would you expect those properties to still be isotropic or anisotropic? If you have elongated grains, do you think the properties would be the same in
No.
the,
No.
right, anisotropic? Perfect. So then if you think one step further, if I said, oh, I take a sample and I anneal it, isotropic or anisotropic properties? ISO, perfect.
Isotropic because
And,
the grains will reform. So
right. And now if I take a material and I cold work it, what do you think is going to happen to the properties? Isotropic or anisotropic?
anisotropic.
Yeah, and in particular, I should probably say like I cold work by drawing in one direction, just to make sure that we get an anisotropic structure. Cool. And then we talked.
One question is for like related to this on the homework. Is it possible to like decrease the grain diameter from 0.04 to 0.01 through cold working?
No,
Okay, yeah, that's
I
what I
mean,
thought.
because you could. No, because that would involve compressing a material, right? Like, and that's not probably going to happen to that extent. I mean, or if you draw it out, you'd be lengthening it in one direction and shrinking it in the other. But yeah, no, like it would be a non-uniform structure. But is that I forget, was that a problem due this week or last week? I
This
get.
week, so like number 4 is an
Yeah,
undeformed
okay.
samples, and you have been tasked with reducing its grain diameter to 1/4 of what it is. Is this
Yeah.
possible?
So that question is interesting because, so if I just have a big grains like a 0.04 or whatever it started at, some higher value, why don't we just do this one together? This is a good problem. And then those of you that are here, if you haven't done your homework yet, you can get an answer. It's a win-win for all of us. Okay, so we have this sample. It has some larger diameter grain, and we want to make it smaller. So we start with these nice equiaxed, say 0.4 millimeter or 0.04 millimeter grains, whatever the problem said, and we want to make it smaller by a factor of 4. What are you going to do?
Cold work it at room temperature and then anneal it at a higher temperature to get
Perfect.
recrystallization.
And why? This is awesome. And why did you cold work it first? Why didn't you just anneal it?
Because annealing normally increases grain size.
Yeah. And why then, if you cold work it, I see that Charles has kind of typed the answer out, but why, if you cold work it, does it promote smaller grains? So when you're annealing now, you're not just getting grain growth, but what are you getting? Yeah.
Recrystallization.
And what's the driving force for recrystallization?
Diffusion.
Hmm.
No.
The energy
No.
between the new crystal and the interface of the old crystal.
Kind of. So Charles in the chat said you cold work to introduce strain. So if we have these grains that are highly strained, Are they high energy or low energy compared to an unstrained grain?
High energy.
Yeah, so the driving force is the formation of these new stress or strain-free grains. So so yeah, you have to have this. So you have to have these dislocations or this high strain in the material to promote the recrystallization process. So good. Thanks for bringing that up. Does everyone feel comfortable with that discussion? Any questions on that? Good. All right. Cool. All right. So we've sort of done.
On the similar manner, what's the driving force for grain growth? I think that is it's diffusion for that.
No,
Oh,
it's so the the does anybody know what's the driving force for grain growth? So the driving force always is going to minimize energy of something, right? So if your grains grow, what energy are we minimizing?
Grain boundary energy.
Yeah. So as our grains grow, we have less grain boundary area in our sample and we lower the energy that way. So diffusion is more of a mechanism by which it occurs, but it's not the driving force. So, as you all know, if you don't know why something happens in material science, the answer is it minimizes the energy. That's always the answer. It minimizes the energy, and that's why it occurs. And then you just have to figure out why the energy is being minimized as you go from A to B. All right. All you need to pass thermo. Yep, it minimizes the energy. Of course, you may not get full credit for that. So, last thing I need is Dr. Butala to tell me that all the students just wrote energy minimization and said I told them to do it. So please don't do that. Do not just do that. But that's an easy way to figure it out, right? Is say like, okay, well, I know that grains grow. That means the energy has to be decreasing. What's that driving force? And you can potentially work back to get that, oh, it's the grain boundary area that's going down. So, all right. We have single crystal versus polycrystalline materials and how that affects properties. In general, single crystals are going to be anisotropic. Polycrystals tend to be isotropic. And of course, we already talked about how the processing can affect that. Poisson's ratio, that's the ratio of strains in our lateral versus longitudinal directions. And I'm just speeding up here, not because of lack of importance of some of these topics, but because where time is dwindling. But of course, feel free to still ask questions if they come up. Stress strain curves, be able to identify all of these things: modulus of elasticity, yield strength, tensile strength, failure strength, the ductility, percent elongation. I think these are things hopefully a lot of you are all pretty comfortable with because you've seen them a number of times before. Moving into strength, we realize that there are tons of ways that we can discuss strengths. Some of them were mentioned up above: our yield strength, our tensile strength, compressive, flexural, ultimate, fracture, or theoretical. And we kind of walked through a number of these, in a lot of the discussions, in some of these strengths, we focused a little bit more on some of our ceramic materials as opposed to metals, but we, some of it's applicable to or relevant to both. But theoretical strength, that's just strength to break bonds. Flaws, these act as stress concentrators. So I would know, what types of flaws would be more or less catastrophic, which ones concentrate stresses more, and those are going to be ones that are bigger and with sharper curvature at the crack tip. The sharper the crack tip, the higher the magnitude of the stress concentration. We talked about different fracture strengths, including the Griffith fracture strength, and then also different factors that affect strength reduction, which we sort of just talked about there. We talked about flexural strength for ceramics, 3-point or 4-point bend test. They have slightly different formulas. We do these because most ceramic samples are too brittle to test using a typical sort of tensile test mechanism. We then talked about our fracture toughness, And this is where we really look at like, okay, we have materials, they have flaws. What's the magnitude of the sort of stress intensity or the concentration? The fracture toughness has these kind of squirrely units of megapascals per square root meter. We spent a lot of time talking about mode 1 fracture toughness, where the mode has to do with the manner in which the crack is opening. So mode 1 is just your crack opening like this. You can think about it, it's your, gator chomp style of crack opening. It's in tension. Plane strain and plane stress, we talked about those types of things. I sort of alluded to this above, but looking at the effects of crack length. And this is just something to keep in mind, that when we talk about crack length or crack dimensions, it's 2C if you have a interior crack, and it's just the length of a surface crack is that key crack dimension. So something to be mindful of and keep in mind, and make sure you're using that appropriately in your formulas. We talk about a critical stress intensity factor. John, C over 2, I'm not sure what you're, no, there. So I would think about, maybe I misspoke, but 2C would be the entire length of an interior crack, and C is the length of a surface crack. So you could think about C as being the radius almost of that ellipse in the surface crack. Or okay, everyone good on that? Anyone not okay with that? Okay. Then we talk about the critical stress intensity factor. Whenever you see critical, that means that's the stress intensity, or that's the thing that's going to be reached when you get failure. Okay, so critical stress intensity, that just means the stress is intensified enough that you're going to get failure of your material. The crack will propagate and the material will fail. We talked about ductile versus brittle behavior. And then, jumping back, toughness is really a measure of the energy a material can absorb prior to failure. So ductile materials can absorb a lot of energy, and that energy goes into the movement of dislocations. Brittle materials, they don't have dislocations that can move. So we were able to look at even some metals, and we had that, that's misspelled there, sorry about that. We looked at the fracture toughness, or the impact testing plot, and then looking at, well, when would we determine or decide that something was brittle or ductile? All right, any questions? I know I'm going a little quick just because I want to make sure we get done with this during the class time.
Okay, another question, like for all these strengthening mechanisms, how are dislocations involved in grain size reduction?
So we're going to get to that. Let's
sorry.
that's a little further down on the thing. So
Oh,
we'll be there in just a moment.
Yeah, by the way, I know that for this week, I only see 11.1 on the, do you think maybe you had some more videos, but they were hidden, or?
No, because that was for last week. So I prepare the videos per our number of meeting times that we would have in person. So last week, because of the Thanksgiving holiday, we would have only had a single period on Tuesday, and Thursday was a holiday. So I'm not going to give extra content just because we're not meeting in person and have extra burden on you all as students than what would be the same as if we were in person. And the lecture was a little short, as I said in the beginning of that lecture, because it just seemed like it was the right place to wrap up, as opposed to partially starting a new topic that we wouldn't have time to finish this semester. So, okay. So the next thing we talked about was deformation of ceramics. And of course, there are some scenarios where we can get plastic deformation in ceramic single crystals, which is basically, when pigs fly and you find some conditions where a dislocation can actually move in a ceramic material. The only ceramics you'll ever see really well, I don't want to say that. You're more likely to see dislocations move in something that's more ionic than something that's more covalent. And we talked about the effects of symmetry. And if you for some reason find yourself with a ductile ceramic, which you're probably not really gonna happen, they could be strengthened in the same manner as you would a metal, and we'll get to that in just a moment. Polycrystalline ceramics, they're pretty much going to be brittle. And then deformation of metals, we've talked about this a lot. It happens, plastic deformation happens because dislocations move. We've talked about slip. We've talked about slip systems a lot this semester. So when we talked about plasticity of metals, if you had single crystals, we had resolved shear stress versus critical resolved shear stress. So resolved shear stress is just saying, oh, I've got some slip plane and some slip system. What's the resolved stress in that plane? Critical resolved shear stress means the stress in that plane is now high enough for a dislocation to move, okay? And that corresponds with yielding. So that's when your conditions for slip are met. Polycrystalline samples, deformation occurs first in the grains most favorably aligned for slip. And then, of course, the deformation continues due to the motion of dislocations. We also briefly talked about another mechanism of deformation, which is twinning. And you'll learn a lot more about that when you all take your mechanical behavior course with, excuse me, Dr. Kraus. So now getting to what Peter had mentioned, strengthening mechanisms. So if materials deform by the motion of dislocations, if you want to strengthen a material, you just need to make it harder for dislocations to move, right? So now if you do solid solution strengthening, why does that make it harder for a dislocation to move? So if you have an alloy, that means you have some solvent atom, that's your host, and you have a solute, that's what you alloyed with. And you have these impurity or these alloyed atoms that are slightly different size. So if they're a little bit they could be too big or too small. So they can preferentially, if a dislocation comes up to one of these atoms, they can, depending on their relative or where they're located, they can relieve some of the strain energy. So, in that open spot below the half plane of atoms and edge dislocation, it's a little bit roomier. Those big atoms, the bigger solute, would fit quite nicely there. It relieves some of the strain energy in the system, and that makes it harder for the dislocation to move. And there's some images of this in in the slide. So decreases the strain energy of a dislocation, then they're pretty content. They don't want to move. Grain strengthening. So if I have a grain and my dislocation sort of happily moving along on a slip system, it's chugging along, and then it gets to a grain boundary, what happens? Well, it's not very likely that there's going to be a slip system at the same spot on the other side of the grain boundary. So that dislocation is kind of going to be like, I don't have anywhere to go. I'm stuck. So dislocations tend to pile up at grain boundaries. And then as you start getting more and more dislocations in your system through this dislocation pileup, it's going to be even harder for them to move or even to generate them because you already have such high strain energy, so many dislocations in your system. And that kind of leads into strain hardening, where the more dislocations you have, the less likely they are to move because they don't want to come near one another. Good? And then we talked about annealing, recovery, recrystallization, grain growth. You probably noticed that we talked about these types of things as we went through the study guide and how they affected, perhaps the microstructure and then the properties. So the fact that it's come up so much probably will give you a hint as to whether or not you'll see that on the exam on Thursday. And with that, we are 1 minute before 9:20, which is when the class period officially ends. So are there any additional questions? Charles asked, for finding the yield strength, should we do a 0.02 offset or just see where the graph starts curving? I think it would, if I would probably try to specify, or if I wanted that level of precision, but knowing that it's where you go from sort of a linear to a non-linear behavior. So I'm kind of giving a non-answer, but I'd probably be pretty specific if I wanted one or the other versus sort of a ballpark idea based on non-linearity. Other questions? Jason, you unmuted, I
Yeah.
think.
I had a question about the like frequency effects on the polarization.
Mhm.
So like if you like were to like graph like frequency against like polarization and you had a material that like exhibited like a bunch of them, like all four, or maybe just like three or two, but like would you see like sharp drop-offs at different frequencies, or would
Yeah.
you see like pretty consistent, like it would
No,
be
it's
more
a sharp drop. It's almost like looks like a step. And I think there was a slide on that back in the electronic properties. But yeah, it's like orders of magnitudes that drop off
All right.
as you transition between them.
All right, thank you.
Yeah, no problem. Any other questions? Well, as questions come up, I'll be in the Zoom for office hours for the next until 10:30. Be back again tomorrow, 4 to 6 p.m. And I'll try to, if you email in the meantime, I'll do my best to get back to you within at least a handful of hours. My schedule is sort of a disaster of meetings right now, but I'll do my best to respond as quickly as possible. All right, well, have a good rest of your day, everyone, and feel free to stick around if you have additional questions.